Good morning, everyone. How's everyone doing today? Awesome. That's a lot of energy. Again, how's everybody doing today? Good. I mean, the only reason I asked this question is so that we could give feedback back to Ori because you all have come back from his keynote. And if the energy wasn't strong enough, we need to tell him that he needs to do something peppier next year. So my name's Hiren Bhinde. I lead product management at Qualcomm for our XR technologies. And just before we get started, I just want to talk about a couple of things. When we decided to give this talk this year, one of the things we realized is that there's so much excitement about AR and VR and MR and all encompassing under this umbrella of XR. But the challenges of doing anything in a standalone device goes highly unnoticed. Just like using a smartphone today, there's so much that works internally that we are not aware of. We wanted to bring some of those to your notice here and just to give you a glimpse. How many developers do we have in the audience? Awesome. How many people here are aware of Qualcomm not only as a company, but its role in XR? Okay, so that's something that we got to fix. We want to make sure that you guys realize who we are and our role that we've been playing as well as a part of the AR/VR community over the past 3 years. So let's get started. But XR, we call XR, one of the terms that we adopted from Kronos over the past 3 years. XR is extended reality, an umbrella term that we use industry-wide that encompasses everything in the spectrum from real reality, that we're seeing each other today, to the other spectrum of virtual reality where you're occluded from the real world and you're completely immersed in the virtual world. We at Qualcomm strongly believe that XR is the next mobile computing platform, and we have been taking one step at a time to push the technology boundaries to make that happen. Now, as we know, XR devices come in many form factors. At one end of the spectrum, there's the devices that are tethered to a PC. Excellent experience, but you are confined to a room. You can get entangled in wires, and they're not cheap. At the other end of the spectrum is also slot-in devices. There are slot-in devices that come in at really low prices and with horrible experience, but we also have really good experiences with Samsung Gear and Google Daydream with Pixel, but you need to have a smartphone in the slot-in device. And then there's the standalone devices, which have become more, which have become more prolific over the past couple of years. And those devices are the ones that we've seen Oculus Go recently, Lenovo Mirage, and HTC Vive Focus. And the beauty of these devices is that you get premium and high-quality XR experiences in a standalone device. You're not tethered to wires, and you don't need a smartphone as well. Now, these devices come in many form factors, but we are focused. One of the things that I'm going to be talking more about today is from the standalone device perspective, which is the third segment. Qualcomm's forte has always been being truly mobile. When we say mobile, we don't mean carrying a backpack on your back and having wires to your head, but being just truly mobile, just wearing a headset. And before we get into some of those details, I'd just like to show you a quick glimpse in our role so far.
You got to just say you love
reason I wanted to start with this particular video is to show that this is the future. The devices are going to change. The devices are going to get more sleeker, lighter. But XR being truly mobile is the future. We're going to start seeing folks using devices in just not their rooms or living rooms or gaming rooms, but all over the place, in a train, in a plane, and some of it we already see, but that's going to be the eventual future to take this mainstream. At Qualcomm, when we started thinking about XR, we took a step back and said, what are the experiences that we want to have our end consumers enjoy? And took those experiences and translated it to key technologies. And these were the three key technology pillars: visuals, audio, and interactions. In visuals, we wanted to make sure that an end user gets excellent amount of graphics pixel quantity and clarity. At the same time, for sounds, not only should one have the ability to hear as if he's hearing in a real world. I think all of us know that George Lucas famously says that 50% of the movie experience comes from the way the music and the sound of the movie is. And that's all because of the way the object-based audios work. So we wanted to have that experience as well. And last is interactions. It all starts from the moment, excuse me, it all starts from the moment a person's born. Right? You have a new baby. The first way the baby starts interacting with the world is by head movement. So head tracking, eye tracking, hand tracking, body tracking. These are the kind of interactions in the real world that needs to be encompassed as a part of the virtual world. So these are the three technology pillars in which we translated the end user experiences and started focusing on that. Today, I'm going to be talking about the interactions pillar, which talks about head tracking. And within head tracking, we'll talk about some of the technologies and how it has evolved. Visual head tracking is a fundamental ingredient to make XR mobile XR. I think you all came here to discuss about SLAM, but we're going to talk a lot about cakes. How many people here like cakes and cupcakes? Really? Everybody on a diet here? Again, how many people here like cakes and cupcakes? Thank you. Well, the thing is that when we started putting these slides together, I was late for one of my deadlines, and on a Saturday morning, before my kids went to one of their classes, I was making pancakes for them. And I forgot to put eggs in it. And the pancake didn't turn out to be a pancake, and my kids weren't very happy about it. So that's when I went up and looked, why is egg such an important ingredient in pancakes? I'll get back to XR and head tracking, I promise you. It turns out that there are two kind of key ingredients. There's one kind of key ingredient which is all about colors and flavors and adds taste. And then there's the oil and eggs, which actually acts as the binding agent and makes it as a well-structured form that gives to the cake as well as cupcakes. And that's exactly what head tracking is all about. The devices might look cool and sleeky, and you have awesome displays and a fantastic Snapdragon SoC in it, but then you need the software to be really, really well. For the experiences that all of you or most of you here in the room are going to build, we need to make sure that the software works well, the tracking works really well. And that's why 3DoF or 6DoF or SLAM becomes a very crucial ingredient as a part of this overall product that we are making to make the end user experience really successful. So let's get into some of those details there. How many people here know what's 3DoF and 6DoF? Okay, excellent. So I don't have to spend much time on that. 3DoF, you're in a room, you look at the world around you. 6DoF, you can not only look at the world around you, you can move in the world around you. I'm going to give have an example that we could use through the end of the session. Let's say you put on a VR device and you're in your conference room, but when you put on the VR device, you find yourself in the middle of Manhattan, looking at the Times Square building. On your left, there's the McDonald's store. On the right, there's the Hard Rock Cafe. So there's a McDonald's store, there's a Hard Rock Cafe. You're looking at the Times Square building. You look around the world, it's 3DoF. You can move around the world, it's 6DoF. Now, 6DoF allows developers to bring the user into the story, because in 3DoF you can just view the world, but in 6DoF developers have a phenomenal way, although it's a new kind of challenge that we've not seen before, but very new, interactive, and challenging ways to become a part of the story and now interact in the story in different ways. So how does this actually work? Now, for traditional PC-based devices, there are external sensors like lighthouses that show where the user is in the room. The information from those lighthouses are sent back to the PC, and from the PC back to the HMD on where exactly the location is. However, in a mobile standalone inside-out tracking, VIO is used for rapid and accurate 6-DoF pose. What it really means is that you need to have all the magic happening in the standalone device itself. The evolution of standalone XR visual head tracking that we have been a part of and have led through within the industry by working with close partners like Google, Oculus, HTC Vive, not only on smartphones but also very recently on standalone devices, started in 2016 with providing a 3-DoF experience, going to 2017 with just a VIO 6-DoF experience, and 2018 is where we introduced VIO plus SLAM. The evolution of the standalone XR experiences this year comes to a point where we've able to provide SLAM, which is simultaneous localization and mapping, or also what we call as room scale 6-DoF. We're able for the end user to walk around in the room. Now, let's get into some insights into SLAM. And what my objective, as I said at the beginning of the talk, is to give all of you 3 key insights. What is SLAM? Why was the need to have SLAM? How does it work? And what are the challenges, not only in SLAM, but specifically for standalone devices? If we leave an agent, say a robot, and let's call the robot Mr. Awesome, in an unknown location, in an unknown environment, can the robot actually make a satisfactory map while simultaneously being able to find its own location in the map? Okay, what does this mean? Let's say you're in a room, you're blindfolded, you're sent to a new room, there's some furniture in the room, or it's an open empty room. How do you know where you are in the room and what's the map of the room? If somebody comes here blindfolded and starts walking in the room and touches a chair and says, okay, there's a chair 1, I want to understand where I go, goes in the front, touches a flower vase, and knows that there's a flower vase here, there's a chair there. There are 2 things that are happening here. The person needs to understand where certain things are, and then secondly, remember where those things are. Again, 2 things. Where those things are, and remember where those things are. Let's say a robot, and if you see our Mr. Awesome's eyes here are actually a camera sensor. So let's start by discussing Mr. Awesome's problem and then go to the glasses. The solution to this problem that we see in the real world for human beings is very intuitive. You walk into a room or you walk in on a street for the first time, you know where you are, you look at landmarks, you remember them, and then you keep walking. That's the kind of experience that you want an end device to remember as well. So there are different solutions. There's, of course, this VIO, structure from motion, SLAM, and we could talk about this for hours, but I'm going to give you a very high level on how this works. First of all, from a camera, when an image is taken, let's say it's a smartphone where structure for motion is being used widely today, the image is a 2D image, but a single image has no 3D information. There's no projection of the 3D world on a 2D image. So that's why the way the cameras will work is I'm standing here, I see this gentleman, I understand where he is, the camera moves to the right, sees the same gentleman, and triangulates the information on how much has the camera moved. Again, starting at point A, go to point B, I see how much the distance has moved, and that's the kind of information the camera triangulates from position A to position B. It tracks the distance, although it's not at absolute scales, it understands what the distance is. The example I gave is of the gentleman sitting here. However, the cameras needs to have intelligence that it cannot track people or any moving objects in the room. It has to track what's called as features, and these features are not moving objects, but they are edges of a window frame or edges of a bed or edges of, let's say, chairs, but features that can be tracked well enough and triangulate information from there. Now, where is the two kind of informations or like multiple images that are taken to recover 3D images? There are two things here that needs to happen. First, it needs to understand where is the position of the camera. Is it point 1 or point 2? And then what are the features that are being tracked here? That's the problem that needs to be solved. While this problem solved of tracking, there's one problem that remains. We solved the problem of tracking using this camera motion in what's called as VIO, but there's one problem that remains, and that problem is the 51st dates problem. Anybody seen this movie? Okay, guys, if you've not seen this movie, we got to talk about something else. Have you guys seen this movie? Anybody here? Drew Barrymore, Adam Sandler? Thank you. You guys don't eat cakes. You guys don't watch Adam Sandler movies. All right, so the 51st dates. Quick 30-second segue into this movie. Adam Sandler is trying to woo Drew Barrymore in this movie, and Drew Barrymore has a car accident, and she forgets every single day what happened in the previous day. So she's stuck on Jan 15th, 1998 or something like that, and she doesn't, every day she wakes up, she thinks it's Jan 15th. She enjoys the day, it's her dad's birthday, she goes around, does groceries, eats her favorite pancake, comes back home, sleeps, wakes up, she forgets her life, she's back at Jan 15th. The key thing here is the Drew Barrymore problem or the 50 days problem was every single day starting at the same point and starting all over again. Forgetting. There was no memory. And that's the problem with the tracking. The way the camera works is I'm seeing the chair here, I'm seeing the chair here, I'm seeing the chair here, but I have no memory of what has happened in the past. And that's the problem that needs to be solved, which is solved by SLAM, which is simultaneous localization, tracking, and mapping, which is the computational problem of constructing or updating a map of an unknown environment while simultaneously keeping track of an agent's location in it. So let's take a start. Let's see what you've learned so far. We need to understand not only where we've been so far, but where we are in the room. If you go back to the previous example that I gave of the person walking in the room blindfolded, trying to see where he or she is in the room, he needs to not only know, okay, I've touched the chair, I've touched the podium, I have a vase. Now I know that I'm somewhere between the vase and the podium. The mental map and constructing that map in the mind is something that we make the cameras do. That's what SLAM is all about. Now, going to SLAM, in summary, the first one, if you see the red triangles, is the camera poses, and the 3D points is actually the features that are being tracked in the room. And there's no relationship between these camera poses, there's no memory, but with going to SLAM, you not only are tracking, but you also have a camera trajectory which keeps a map around for localization. And it must operate in real time. And so there are some design challenges with it that we need to see. So what are the SLAM design challenges? And why am I going into some of these design challenges here? One, imagine wearing a standalone VR or AR glass, walking in the room, being able to construct the room that you're walking in for the first time and having an experience, and the device needs to continuously update and have a good location, a good understanding of where you are in the room. So it needs to happen real time. So the key design challenges are, one, it needs a map for localization. Second, it needs to happen real time, as opposed to some other methods where you could do it offline. This needs to happen real time. And third, that there's very limited operation time and limited amount of data, which translates to, although I might get all the features in this room with different chairs and the camera tripods and the speakers, the system also needs to understand what needs to be remembered, what needs to be dropped. And so there's different methods that it can be done. But this is kind of the summary of what are the design problems that needs to be solved. So in this picture, if you look at the features that are in the corner of the room, it's just an example of how these features are tracked. Okay. Now, what are the benefits of SLAM plus VIO head tracking? First is environmental mapping. As I said, we've discussed this for the past few minutes. How does environmental mapping really work? Okay. All right, there was a video that was supposed to work, but it did not. Let's look at this particular animation that we have here, and hopefully this works. But let's say this is the room that you're tracking. Somebody comes in with a glass, and again, this is a very theoretical, pictorial view of how this SLAM might work here. Okay, I think there are some problems with the, is it possible for you to play this video, sir? Excuse me. Is it possible for you to play this video? All right. Hopefully it plays. These are the glasses, and that was the room. Now in VIO, as you keep looking at the room, there's no past memory of where you're looking at. But in SLAM, as you keep looking at the room, the device has a memory of where you've been. Again, this was a very high-level conceptual view of how it works. I'd also like you to see if you can play the video on this screen, sir. Awesome. So you have the VIO glasses, you look in the room, there's different features that are being tracked here, but there's no memory of what the room's seeing. At this time, the VIO glasses is just looking and tracking. However, using SLAM, as the glasses are used to look around the room, the glasses itself has a memory of how the room is mapped. And that's one of the key benefits of SLAM. And the reason this helps is that you could actually take this a step further and construct a virtual world in the room that you're in. But more about that later. Second is relocalization. Imagine walking in a forest and having no landmarks. And then imagine walking in a forest and having landmarks. Goes without saying, in the latter case, you know where you are and where you're able to, where you need to go based on the position that you know. But isn't this something similar that we discussed before? No. It's actually subtle, but it's very important to understand. The reason is, I was talking about the features earlier, that when you wear AR or VR glasses, you're tracking the features in the room. Now imagine you look at a wall, a white wall, there's no features to track, the device has no memory, it does not remember, and when you come back and you look at the same chair or the gentleman or the tripod, it's looking at the same features, but it doesn't know what it's looking at, and it doesn't know where it is in the room. So if it would have had the past memory, it can start immediately at the same place and just readjust itself. So this relocalization is extremely important, not only to save on a lot of compute power, but also mainly to have the right kind of experience. And it's extremely crucial for developers, by the way. It's really crucial for developers because once the relocalization problem is solved, if the user looks at the ceiling, which is a white wall, and then looks back in the room, if the experience falls apart, the virtual world's just going to fly away or drift, or there's going to be some sort of problem where the end user is not going to enjoy this experience. So the first benefit was environmental mapping. Second is relocalization. And third is bounded drift, or what's called as no swim effect. Let's say I'm wearing an AR glass, I'm playing chess, I'm playing virtual chess on a real chessboard, and I look around, I look back, and the chess pieces have moved. That's a game that I'm definitely never going to win. So this is an experience that will, this will actually, for the lack of a better word, really drift the experience that you want to have. So the swim or the jitter effect here is something that's solved by SLAM, because in SLAM with the memory, the drift is bound, and that's the problem that's solved. Those were the benefits of SLAM. But what are the challenges, other than the design challenges, what are the challenges of SLAM in a visual head tracking system? when you're wearing glasses. First, if it's a featureless environment, if it's a nice white room, no furniture, there's no features to track. If there's a lot of bright white light on the camera sensors, it's going to be difficult to track. Last but not the least, if I'm looking at a glass, if there's shadows, if there's reflections, then I might be tracking wrong features. Those are the challenging environments. We recently did a very intensive research study on one of our, the SLAM that we made on Snapdragon 835, and we found some really interesting insights out of, specifically from the lights and glass area. One of our colleagues who actually went around and did that experiment, and he did it in trains and in front of mirrors and in low light environments. It was amazing to see that in some of the environments, even at low lights, how 6-off and would work really well. But if there was really bright light, it would just lose any sort of tracking capabilities. There's, of course, different sort of lux levels where it works and does not work in these challenging environments. How do we solve this problem? When we make glasses, we use wide-angle lens, or we use a monochrome sensor with a very good superior dynamic range to track features really, really well. We also use high-speed IMUs, accelerometers, and the whole IMU subsystem that runs at really high refresh rate to take the camera information and the IMU information and run it through the algorithms where the magic really happens and provide what's called as the head pose. So going back to the New York example, in the virtual world, if I'm looking at Manhattan, at the Times Square building, and if I look left, right now in the real world, when I look left, I can see the speakers. I'd expect to see the Hard Rock Cafe or the McDonald's immediately on my left. And for that, the device needs to send deep pose information. Device needs to get the pose information immediately to reflect the right kind of graphical information, the right graphics, the right visuals, the right sound, the right hand or controller gestures, immediately all back to the application processor in less than 20 milliseconds. And that's what constitutes as the foundation of what we call as motion to photon latency. It's an industry-wide used term, and scientifically it needs to be in less than 20 milliseconds. All the Snapdragon's subsystems right now, 835, 845, are at sub 20 milliseconds at about 16 to 18 milliseconds today. Other than this, there are some head-worn device challenges specifically for visual tracking as well. And why does it really impact? I'd like to imagine this is the kind of the glass that you're going to wear. And for those glasses, all right, going back to the previous slide, I'm going to call you Mr. Awesome. Could you help play this video, sir? All right, so let's look at this video. In these glasses, there's a very tiny Qualcomm Snapdragon SoC that helps power the engine of the device, right? And now this device has a visual processing subsystem and a DSP and a camera ISP, the audio DSP, the CPU, of course, and memory bandwidth. And all of these are going to be exercised together to have an end XR experience. And when you have that, it's like, the best analogy I can give is running on a treadmill at an extremely high elevation with, say, 40 pounds in each of your hands and tied to your legs. You're putting the processor to go through really rigorous, intense exercise at this point. What happens because of that is that the processor can become really hot, and your battery life could be less. There could be a lot of heat that could be dissipated. Imagine having a smartphone in your pocket that becomes hot and you get uncomfortable with it. Imagine having a device now right in front of your eyes and having similar issues. But that's the problem that Qualcomm has always looked into and solved, because power and thermal management has always been our forte. There's a fun video that I'd like to show you that we did a few years ago to show how Qualcomm's played a role in this. Mr. Awesome, can you play the video for me, please?
Thermal efficiency has become very important because from an end user's perspective, the phone or the tablet that a user is using gets so hot at times that it becomes annoying. We have 3 devices. a Qualcomm-based phone and two competitor-based devices. The thermal camera shows the thermal footprint that the three phones leave when running a CPU-intensive test. One way to show the results is via a heat map through a thermal camera. What we are trying to compare is thermal efficiency when the CPU is delivering peak performance. As you can see, the phone based on Qualcomm's chipset is much more thermally efficient compared to the competition. Another way of showing results is by melting butter. Yeah, melting butter. Butter melts at 35 degrees Celsius. As you can see, the phone based on Qualcomm's chipset is much more thermally efficient compared to the competition. One of the phones that is heating up the most is heating up to 55 degrees Celsius. That's hot, that's really hot, and you can perceive it on your skin. Qualcomm Snapdragon S4 is the coolest kid on the block, and we mean it literally.
So power and thermal efficiency is essential for XR. And the challenges of XR workloads are that they're really compute intensive. There's a lot of complex concurrencies. It's always on. It's real time. And it's in a very constrained mobile variable environment. It has to be thermally efficient for sleek devices and designs. The cool kid on the block, the Snapdragon device, the Snapdragon SoC has some of the cool devices powered today by Snapdragon. So the Oculus Go, the HTC Vive Focus, and the Google Lenovo Mirage Daydream device are all powered by Snapdragon today. We discussed today about VIO, SLAM, some of the design challenges with SLAM, and some of the design challenges with a head-worn device itself. This is just the beginning. As I said, Qualcomm's is a part of this long-haul journey, taking one step at a time to design, to resolve all the design problems or the technologically challenging issues that might come across on this path, and take each step to keep pushing this space forward. This is how we visualize the world in the next couple of years on how the XR devices can be used. But more about that, maybe next time. You wear an XR glass, walk into a room, you map the room, but then you can also see and use the devices or the objects in the room and use them for a different kind of a virtual experience. More about that next time. Thank you very much. Appreciate your patience.